Hello everyone, I am Lavanya D, a PMRF scholar from IIT Madras. I welcome you all to the Week 9 live session of the course Material and Energy Balances. In the Week 9 videos of the course, we would have looked about psychrometric charts, also called as humidity charts. These are nothing but cross-plotted charts that gives information about liquid, vapor and mixture of these two phases. So basically information on dry bulb temperature, moisture content, relative humidity, dew point, humid volume, wet bulb temperature, specific enthalpy, enthalpy deviation and so on. Finally about mixing and solutions. Let's look at the first problem on psychrometric charts. List all of the properties you can find on the humidity chart in AE units, that is American Engineering units, for moist air at a dry bulb temperature of 90 degree Fahrenheit and a wet bulb temperature of 70 degree Fahrenheit. It is reasonable to assume that someone could measure the dry bulb temperature using a typical mercury in glass thermometer and a wet bulb temperature using a sling psychrometer. So these are the ways in which you can measure a dry bulb temperature and a wet bulb temperature. Solution. So here we will refer to the figure 8.42 in the book Felder and Rizzo, title Psychrometric Chart American Engineering Units, and here the reference state is H2O, liquid phase 32 degree Fahrenheit 1 atmosphere, dry air 0 degree Fahrenheit 1 atmosphere. So I have given the psychrometric chart picture here, which is an American Engineering units. Based on this, let's solve the problem. So they have asked us to list all the properties we can find on the humidity chart. So a simplified version of the psychrometric chart in American Engineering unit is given here to solve this problem. So let's find all the properties one by one. So first, TDP. TDP is dew point temperature. So dew point, the dew point we will find when is a temperature where the moisture begins to condense. So this point we will find when we draw a vertical line from 90 degree Fahrenheit, and when you extend the line horizontally around this point A. Point A we will get when we draw vertical lines from 90 degree Fahrenheit and 70 degree Fahrenheit. And extend it till 70 degree Fahrenheit. So this is the point A. At point A, when we draw a horizontal line till the saturated air line and extend it down, we will get the dew point. So when the air A is cooled at constant pressure, it will eventually reach a temperature at which it begins to condense. So that is the dew point, and that is at 60 degrees Fahrenheit. Next property that we will find is relative humidity. So we know the point A lies between relative humidity lines 40% and 30%, that is given here. So by interpolating it, the point A is found to be 37%. So relative humidity will be 37%. Next property is humidity. So humidity we can read from the right hand side axis. So this is point A. When we draw a horizontal line till the right hand side axis, we will get a value of 0.012. So this can be written as 0.0112 pound H2O per pound dry air. So humidity is always written per pound dry air. So if 1 pound of dry air is there, in that 0.0112 pound of water will be, H2O will be there, the moisture content. So the next parameter that we will be finding is the humid volume. So the humid volume we will again be finding by interpolating these slanting lines. So which you can see here in these lines. So these are the lines for humid volume, which has been denoted here with the unit of feet cube pound mass dry air. So the point A lies between 14 feet cube and 14.5 feet cube per pound dry air. So the humid volume will be 14.1 feet cube per pound dry air. The next property will be enthalpy. So the enthalpy value we can find from these lines, enthalpy at saturation. So these lines, these slanting lines will give us the enthalpy at saturation. So from the point A, when we extend to this axis, we will get a del H cap value of 34.1 or 34 approximately. With that, we will subtract the enthalpy deviation value. The enthalpy deviation value we will get from these curves that are given here. So the point 90 and 70 will lie somewhere around here, and this point will lie between this curve and this curve. So the deviation from this curve will first be calculated. Which in this case is 0.2. So this enthalpy will be subtracted from the deviation. So 34.0 minus 0.2 will give us 33.8 BTU per LB dryer. So these are the parameters, and we have found the values for all the parameters. So I will locate the point A in the chart, and so that you can apply all these in the chart and find the values similar to what we have solved. So let us locate this. So if it is 90 degree Fahrenheit, so this will be the exact point A. As we calculated, we can see that the point A is intersecting on the humidity line here, which gives a value of around 0.011. So it is intersecting here 0.011 exactly. .1122. This value we have found. When you extrapolate this point here and when you bring it down, you will get the dew point temperature also, and similarly you can try solving for all the other points. When you extend it here, you will get the enthalpy value of 34, which you will subtract with the deviation and find the specific enthalpy here. So these are the values, and this is how we solve using a psychrometric chart. Any doubts? Okay, let's move on to the next problem. This problem is on energy balance with phase change. Question number 2. When solids pass through a continuous dryer, 400 kg of hot and bone dry air enters the dryer per minute and picks up the water that evaporates from the solids. So air enters the dryer, it dry at 400 kg per minute rate. It picks up the water that evaporates from the solid Humid air leaves the dryer. Now the air contains some amount of water. So this humid air leaves the dryer at 50 degrees Celsius containing 2.44 weight% water vapor and then passes through a condenser. Cooled air and condensed liquid water leave the condenser at 10 degrees Celsius. The pressure is constant at 1 atmosphere through the system. So what they have given is air enters the dryer at 400 kg per minute, picks up the water from the solid that is present, and humid air leaves the dryer at 50 degrees Celsius and enters the condenser where the water vapor is condensed, and cooled air leaves the condenser at 10 degrees Celsius, and the whole system, the pressure that is maintained is 1 atmosphere. This is the information that they have given in the question. So they have asked us to find all these. The rate of water evaporating in the dryer, and using the psychrometric chart we have to find the wet bulb temperature, relative humidity, dew point, specific enthalpy for the air leaving the dryer. So for this air. Next, using the psychrometric chart, we should find the absolute humidity and specific enthalpy for the air leaving the condenser. So this will be for this air at 10 degrees Celsius. And since everything is given in degrees Celsius, kilojoule per kg, dry air and all, the psychrometric chart that we'll be using will be in SI units. Next, the rate of condensation of water. Finally, the rate at which the heat must be removed from the condenser for condensation to happen. So these are the things that we should find. Let's calculate everything one by one. First, we have to find the rate of water evaporating in the dryer. So I have given the picture of the psychrometric chart in SI units here, which is also taken from the book Felder and Rosso. Humid volume, dry bulb temperature, moisture content, enthalpy and saturation, wet bulb, everything is in SI units. So here the reference rate that is taken is H2O, liquid phase 0 degrees Celsius and 1 atmosphere, dry air 0 degrees Celsius and 1 atmosphere. So like they have asked, first let's find the rate of water evaporating in the dryer, which is the A subdivision. So the rate at which air is entering is 400 kg per minute. And in the question itself they have given once the humid air that is leaving the dryer contains 2.44 weight% water vapor. So 400 into 2.44 weight% water vapor to the kg of air that is present, remaining dry air, 97.56. So this value will give us the humidity, and when you multiply this with the air that is entering, we will get the rate at which water evaporates. So the answer will be 10 kg water that will evaporate per minute. So let's write it here, 10 kg. Next, what we will be finding are these parameters. So let's see that one by one. First is the wet bulb temperature. So we will find the wet bulb temperature. Let's go to the chart. First let's locate the point. We note that in the question they have given the humid air is leaving the dryer at 50 degrees Celsius. So let's extend this. So this is the 50 degrees Celsius line. First we have to find, before we extend the line and find the wet bulb temperature, we have to find the moisture content that is present in the air. So let's find that in the subdivision 1. To find the moisture content, that is the absolute humidity which I am talking about, we will just divide this amount of water evaporating to the amount of air supplied. The value that we will get is 0.025 kg water per kg dry air. So this value we have found out, and that value is 0.025. So when we, it is here. So we should extend this line till 0.025. Which is this point. This point that is here. Let's take this point as A. We have found out this point. To find the wet bulb temperature, that is what they have asked in the question first, wet bulb temperature. So can anyone say how this will be found? Okay, so we should extend this point along these slanting lines, which I am showing it in these dotted lines, and this dotted line should be vertically extended down. So along these lines, we will extend it down. So the value that we are getting is 33 degrees Celsius. So this will be the wet bulb temperature. Next is the relative humidity. So relative humidity we will find based on these curves that are given here for relative humidity. So when you extrapolate, this point A is lying between the relative humidity curves 30% and 40%. So when you extrapolate it, the relative humidity at this point will be around 32%. So the answer will be 32. Next is the dew point. Dew point is the point where the air begins to condense. So the dew point we will find out by drawing a horizontal line from this point, from the point A, along this line, again which I am denoting it in dashed lines, which comes somewhere here, and extending this downwards. Or we can find it with the scale that is given in the slanted axis itself. 27, 28, 29, 30. So if this is 29, this will be, if this is 28, this will be 28.5. So this is how, when we extend this downwards also, we will get the same value, which is around here, and that is 28.5. So this will be the dew point. Next is the specific enthalpy. So specific enthalpy we can calculate as we did in the last problem. We will extend the point A along this slanting axis, the slanting axis that is given here for enthalpy at saturation. So when we extend it till here, we will get a point here which will be 116. So 116 will, this value, with this value we will subtract the enthalpy deviation value. Enthalpy deviation value we will get from these lines, these curves. So this point is lying between 1.0, minus 1.0 and minus 1.2 curve, and the value that is calculated is minus 1.1. So when we subtract 116, 1.1, we will get the value of something around 115. So the answer will be 115 kilojoule per kg dry air. So we have found all the parameters for the B subdivision. Any doubts? Okay, let's move on to the C subdivision. Using the given psychrometric chart, answer the following for the air leaving the condenser. So the air is leaving the condenser at 10 degrees Celsius. Now to find the absolute humidity, we will again move on to the psychrometric chart for air leaving at 10 degrees Celsius. The relative humidity that we found is 32%. So let's mark the point at that 32%. So when we mark the point, it will come somewhere around here. So to find the absolute humidity, we will extrapolate this point to this axis, and the value for absolute humidity that we will get here is 0.0077, and to find the specific enthalpy similar to this method that we followed for B subdivision 4, the similar way we will find the specific enthalpy for this also. Please try solving for specific enthalpy by yourself. The answer that you will get will be 29.5. Let's move on to the D subdivision, where they have asked for the rate of condensation of water. So to find the rate of condensation of water, we will multiply the 400 kg dry air into the specific enthalpy change that we have found. So 0.025 which we have found here, minus 0.0077, which is equal to 6.92 kg of H2O per minute condense. So 6.92 is the rate of condensation of water. Finally, they have asked us to find the rate at which heat must be removed from the condenser. So they have asked us to find the value of Q. So based on the energy balance equation, Q will be equal to delta H, where the terms of shaft work, potential energy and kinetic energy will be equal to 0 here. So let's find out the value for Q. So the reference state that we will take is dry air at 0 degree and 0 degree. So let's draw the table here. Substance, moles, enthalpy in, M out, enthalpy out. So the two substances that we will be considering here is air and water. So air in, they have already given 400. There is no water in. So for air in, the enthalpy in is 115, which we found out here. Yeah, the specific enthalpy. For air out, it's again 400, along with moisture content 6.92. And the H out, we found it to be 29.5 here. Yeah, here. And we have to find the H out for water. So let's calculate this. So this can be calculated with the help of first the specific heat value, which is 75.4 joule per mole degree Celsius for water into the difference in temperature, that is 10 degree Cp del T, Converting this into grams, so we will divide by the molecular weight, which is 18 gram, multiplied by joule to kilojoule conversion, gram to kg conversion. So the answer that we will get is 42 kilojoule per kg. So this can be substituted here. Now we have got the table. With these values, let us find the heat, so the formula will be Q is equal to del H, which will be equal to summation of m dot H cap out for any substance I minus summation of m dot Hi cap in, that will be equal to, by multiplying all the values that we have got, minus 34027.8 kg per minute into 1 minute will be 60 seconds into 1 kilojoule per second to kilowatt. So we'll get the answer as minus 565 kilowatt. So we have solved for all these parameters. You can also try marking the point, a particular point in the psychrometric chart, and finding these parameters for various other problems. Any doubts? Okay, let's move on to the next problem, which is on mixing and solutions. So I have taken a problem regarding production of hydrochloric acid. Question number 3. Hydrochloric acid is produced by absorbing gaseous HCl, hydrogen chloride, in water. Calculate the heat that must be transferred to or from an absorption unit if gaseous HCl at 100 degrees Celsius and H2O at 25 degrees Celsius are fed to produce 1000 kg per hour of 20 weight% HCl, aqueous HCl at 40 degrees Celsius. So in the question what they have told us, to produce hydrochloric acid, we need gaseous HCl and water. So gaseous HCl, it is supplied at 100 degrees Celsius and water is supplied as 25 degrees Celsius, which is already given in the question. They have asked us to produce 1000 kg per hour of aqueous HCl with 20% weight percentage of it at 40 degrees Celsius. So first we have to find the flow rate, molar flow rate of HCl and water that is entering the absorber. To find that, molar flow rate is usually found by dividing the weight by molecular weight. So 1000 kg per hour, which is the flow rate, will be multiplied by 0.2 kg HCl by 36.5 kg HCl, which is the molecular weight. So the answer that we will get is 5480 moles of HCl per hour. Similarly, to find the moles of water, 1000 kg per hour into the remaining 80%, that is 0.8 kg water by per kg, the product into 2.3 mole by 18 kg water, which is the molecular weight of water, which will give us a value of 44,400 moles of H2O per hour. So these two values we have found out, and these are the values written in the question here. So similar moles after absorption will be obtained from the product also. So since we have found the molar flow rates, let's draw the table here. Substance, NN, HM, in out, H out. Substance will be HCl, H2O, HCl aqueous. So in we have found to be 5480 moles of HCl. So the unit will be moles, and here it is 44,400 moles, and HCl aqueous is 0. So enthalpy we have to find, which we will term it as H1 cap with units kilojoule per mole of HCl. So this will be 0, this will also be equal to 0. And out, this will be 0, this will be 0, and aqueous will be 5480. 0, 0, and H2. Let's term this as H2, which we will be finding out. So first, we should calculate this H1 cap and H2 cap. To calculate that, first for a H1 cap, let's write the reference state. So HCl, that is in gaseous form at 25 degrees Celsius, is being converted to HCl, that is in gaseous form at 100 degrees Celsius. So for H1 cap, we will apply the formula of delta H cap is equal to Cp del T, and the difference will be from 100 degrees Celsius to 25 degrees Celsius. So for solving this problem, let's find the R value first that sir explained in the video. The R value will be equal to moles of solvent per moles of solute. So R will be equal to 44,400 solvent, that is the water, by 5,480, that is the solute. So the answer that we will get is 8.10. So the equation will be HCl, which is in gaseous form at 25 degrees Celsius, plus 8.1 moles of H2, which is in liquid form at 25 degrees Celsius, will react with a specific heat of del H cap A to form HCl at aqueous form at 25 degrees Celsius. Finally, with the del H cap B, another specific heat, it will be converted to HCl at aqueous form at 40 degrees Celsius. So this will be the reaction with the phase changes. So let's del H cap A can be calculated based on the heat capacity table that is given in Perry's Chemical Engineer's Handbook. You can see that. Here in this table, the heat capacities will be given as a function of mole fraction. So I have given the table here. So this is the table where the heat capacities is given as a function of mole fraction. So this table. Yeah, so from this table when the mole fraction is 8.1, the value will be somewhere around here. So the value that is calculated is delta H is for 25 degrees Celsius and for an hour of 8.1 will be minus 67.4 kilojoule per mole of HCl. So let's calculate the mole fraction of HCl also with the total mixture. So the mole fraction we will calculate by dividing the 5480 moles of HCl per hour by the total, which is 5480 plus 44,400, which is equal to 0.11 moles of HCl per mole of the total mixture. So with the 0.11 mole fraction, we will find the specific heat value for HCl. So all these we are doing to find out this delta HB. So when we know the mole fraction, with that and the specific heat value, we can find the delta HB. So the specific heat is 0.73, that is already given, kilocal per kg degree Celsius. kg by 5480 moles of HCl into conversion of kilocal to kilojoule, where 1 kilocal is equal to 4.184 kilojoules. So the answer that we will get is 0.557 kilojoule per moles HCl degree Celsius. So the delta HB value will be Cp dt, which is equal to dt of 40 degrees Celsius, 25 degrees Celsius. So the value will be 8.36 kilojoule per mole HCl. So since we have obtained both these values, we can calculate the H2 also, which will be equal to minus 67.4 plus 8.36, which is equal to minus 59.0 kilojoule per mole HCl. So finally, we will do the energy balance and apply these values in the formula. These are here. we will get a final answer of minus 3.35 into 10 power 5 kilojoule per hour. So this value will be minus 3.35 into 10 power 5. So this is the final answer. Any doubts? Yeah, this question is from the Felder and Russo. Mexican solution, there are many questions from Felder and Russo. And for psychrometric charts, you can refer this and Hemmer Boss book. If there are no doubts, we can end the session here. Thank you.